So, welcome everybody again to another episode of the ideaXme show, the show that profiles the humans behind the truly big ideas that are shaping the world and the future and inspiring future creation. I'm Ira Pastor, your health, aging, and longevity ambassador. And today we're going to continue our journey through what we refer to as the biologic architecture of health and aging. And we're going to spend some time at the level of both the genome as well as the level of the respective bioproducts that peel off of our genomic knowledge today, not only for the purposes of human health, which is extremely important, the topic of the show, but also connections to agriculture, energy, the environment, as well as some other very novel possibilities, which for now we'll classify as other. And quite a lot has changed since we first mapped the human genome back about 20 years ago. As time has moved on, we've learned so much about sort of the intricacies of the genomic space, how fluid it is, how networked, filled with feedback loops and hierarchies of control, intricate phenomena such as epistasis and pleiotropy and alternative splicing, and sort of the endless array of architecture within the genomic non-coding realm. It's really a fascinating area, and one that we can really leverage to so much possibility moving forward in terms of human enhancement and health. And as such, I can think of no one better to join us in this discussion about these topics than our guest today, truly the thought leader of all thought leaders in both the genetics and synthetic biology space, and that's Dr. George Church. Dr. Church is a geneticist, a molecular engineer, and a chemist. He's the Robert Winthrop Professor of Genetics at the Harvard Medical School. He's Professor of Health and Sciences and Technology at both Harvard and MIT, as well as a founding member of the Weiss Institute for Biologically Inspired Engineering at Harvard. Back in 1984, during his Harvard PhD, this document included sort of the first direct genome sequencing, molecular multiplexing, DNA barcoding, which eventually led to the first complete genome sequence published of H. pylori. He helped initiate the Human Genome Project, as well as the Personal Genome Project in 2005, which today provides the world's only open access human genome and trait database. His innovations in genome sequencing, synthesis, cell and tissue engineering have resulted in literally over a dozen companies involved in medical genomics, synthetic biology, gene therapy, and genome sequencing. Some of the names: Editas, Veritas, Genome, Warp Drive. The list goes on. He's also director of the U.S. Department of Energy Technology Center and the director of the National Institutes of Health Center for Excellence in Genomic Science. Received numerous awards, is author of hundreds of peer-reviewed publications, patents, and a wonderful book entitled eGenesis: How Synthetic Biology Will Reinvent Nature and Ourselves, which, interesting, comes a wonderful tagline in Amazon. A Harvard biologist and master inventor explores how new biotechnologies will enable us to bring species back from the dead, unlock vast supplies of renewable energy, and extend human life. With all that, Dr. Church, thank you so much for coming on the show and spending a little time with us today.
Thank you.
So just for those that don't know you, can you just spend a little time just giving a little bit of your background, how you got interested in science and genetics, and ultimately how you find yourself at the epicenter of sort of the translational biosciences in 2019?
I grew up without any scientists in my life, and I didn't really have any science courses until around 8th or 9th grade. Nevertheless, I was strongly attracted to it, largely, I guess, due to exposure to books with pictures and the World's Fair. And I made tried to figure out what field would allow me to not specialize, and that turned out to be crystallography. Oddly, it sounds very specialized, but actually included math, computers, physics, chemistry, and biology, all in one tight little package. And then I tried to apply that to other fields that weren't so integrated and weren't automated and without computer models, which was essentially the rest of biology and chemistry. And I started doing that as a graduate student in Wally Gilbert's lab at Harvard. and that's just that attitude of integration and of different fields and uh, rethinking the technology, especially technologies that I later learned were exponential. I had a gut feeling that they would move fast, but I didn't really have the concept of exponentiality when I was a teenager. But now it's quite clear that that's what they had in common. That's why a lot of roads end up pointing to that, either pointing in or out from that singularity of these exponentials.
Fascinating. It's been an exciting path. Just reading through your background. It's an independent story all in itself. Before we get into some of the work you're doing now, I just wanted to talk about something. I mentioned a little bit of the intro, which has to do with sort of the exceptional amounts, alongside of all your work, it's sort of the exceptional amount of technology transfer related to biotech startups that you've been spawning throughout your career. And I bring this up, interesting, because I think a lot of the public normally thinks of, sort of most of the stuff gets accomplished in this space by funding by some nondescript governmental agency with some fancy acronym or some independent nonprofit biomedical research institute. But sort of this model, this important cycle of science, technology, commercialization of interesting things that yield wealth and ultimately fund more of that cycle to keep the dreams going is extremely important. Can you just talk briefly about sort of this dual aspect of your career and how, I guess, important it's been in allowing you not just to do the science, but also to achieve all these different milestones, in disparate parts of the industry?
Well, I mean, so I've been doing sort of collaborative work with industry ever since I started graduate school at Harvard. First with BioRad, and then with Biogen, and then soon thereafter with genome therapeutics, and part of the reason that well, I never really left my academic job during all these collaborations. I was briefly one of the first employees at Biogen, but that was brief, and I was intending to do a postdoc at UCSF. And it's somewhat unusual to be involved in so many competing companies. Normally that would be a risk factor for them. But I think it got started by multiple companies want to license our technology, and since I wanted the technology to be non-exclusive, then the advice that went with it was also non-exclusive. And after a certain number of years of that, where they had no choice, it became evident that it wasn't really a risk for them, because I'm fairly good at keeping secrets from the haves, the different components. And occasionally, if I feel that two companies should be talking to each other, I don't like spill the beans. I simply say, why don't you guys talk and see if you have anything in common? And every now and then they have so much in common that one will acquire the other. So this happened, for example, with BGI acquiring CGI, which is one of my favorites, where I was working with both groups, and now they're one of the arguably powerhouses of both sequencing, synthesis, and instrumentation.
Talking specifically a little bit now, sort of going into human health, and obviously, I'm the longevity ambassador on this show. We talk a lot about aging and disease of aging. The longevity biotech space is one that has gotten pretty hot in recent years. I come out of traditional big pharma, and in big pharma there was always sort of a lot of infighting going on between the different therapeutic fields, whether it was cardiovascular, cancer, or whatever, where all the money should be going. Unfortunately, I see, in longevity biotech, I see a lot of this sort of an early stage, and everybody has their theory about aging. They don't want to give up on whether it's inflammation or DNA damage or telomeres or stem cell exhaustion, or the list goes on. And I've been I've sort of been in the camp that says, look, aging is a pretty complex network set of processes. It's probably going to take a lot more than your traditional approach by pharma, that and what I've heard was the little white pill approach. You've spoken a bit, recently, in the gene therapy field and approaches to aging, not just on individual gene therapies, but on combinations. And combinations, in the pharma world is always a tricky business. Big pharma hates it because, they like discrete little things. But when it comes to something as complex as aging, it doesn't make a lot of sense to focus on little components when there's a lot of things happening. Can you talk to us a little bit about sort of the way you think sort of the combinatorial nature of some of these gene therapies, not just as it relates to aging, but also maybe some of the things you're doing in xenotransplantation or embryonic editing, things of this nature, in sort of ways that multiple gene therapies and interventions can control better than sort of the old school pharma single magic bullet model.
There's two components here. One is, what's the minimum number of therapeutic agents to accomplish a goal, and the other is what's the opportunity for multiplexing for either discovery or for accomplishing those goals. In other words, how many things can you do at once? How many do you need to do at once? And there are plenty of examples of combinatorial therapies that work. Most of them are when we're dealing with a Darwinian situation where we have combination therapies for pathogens, microorganisms and viruses, and combinations for cancer. Those are validated. There are also some validated examples of multiplexing, even multiplex editing. So, for example, with CAR T cells, there are about 5 different edits that accompany the CAR T itself. The chimeric antigen receptor is not an edit. It's a fusion protein that recognizes the cancer that's going to attack. But there are many other edits that make it more immune compatible or more compatible with simultaneous chemotherapy. So that's another established component. There are other places where multiplexing, not so much because there are many different things that are in the disease, but there are many different things that are required to achieve the goal of transplant. You could think of it as a disease of transplant rejection. And there simply are a lot of things that have to be solved. You have to get the histocompatibility right. If you just get rid of it, then you have a natural killer problem. So you have to get the natural killer cells to avoid a cell that's missing is, say, class 1 antigens. Then you have to get the sugars right, the complement, and the coagulation, which are 2 cascades in the blood, which are incompatible in pig organ transplant. And then you have to get the safety component of eliminating endogenous viruses and potentially exogenous viruses too. Now, part of or exogenous pathogens. And one of the nice things about a foreign species is some of the pathogens that humans are susceptible to, including pathogens that could be causing organ failure. The pigs are not susceptible to those pathogens. They have their own set of pathogens, but those set of pathogens, they tend to pick up on a pig farm, and you wouldn't pick up in a human. So you might have the best of both worlds where they're resistant to the pathogens they're going to get exposed to, which are human pathogens. But you want to do more beyond that. And one of the cool things about transplantation, the new transplantation, where you're not just, chasing after, organ donors that had some unfortunate brain death accident, where you're actually intentionally building organs, whether they're human lab organs or pig organs, is that you can make something that's better than what you would get from a human being. I mean, a lot of the discussions, can we get something that's almost as good, but you can make something that's quite better, something that has low senescence, low pathogens, low cancer, and so forth. We know how to do that in animals, but just those animals are typically mice. They're not ready to transplant organs. So you have to redo it in pigs. But it's a really incredible opportunity to, in fact, it could get so good that people might want to have organ transplants that don't have failing organs, which would be a remarkable state of affairs. Some of these are just cells, a few cells here and there, you know, some T cells or some islet cells, but there are many opportunities there.
Wonderful.
All involving multiplexing and combinations.
Yeah, I complete agreement with that. And you know, fortunately, I think we're at a place in the 21st century where we're beginning to see some leeway that we don't need. You know, in the past, it was let's look at each of these therapies and then put them all together. But we can start with the combinations, and I think we're going to be seeing some rather fascinating possibilities because of that moving forward. Now, moving slightly sort of into the area of synthetic biology, and for those that are going to be watching and unfamiliar with this term, sort of synthetic biology is this integrated scientific discipline that focuses on either redesigning existing biologic systems for enhanced or novel purposes, or in basically creating new forms of life. You know, technically, some of these early applications go back to early days of genetic engineering, recombinant DNA, and so forth. But looking into the future, you know, a lot of these, there's some really exciting endeavors in terms of transferring entire genetic pathways and circuits between species, like you mentioned, the growth of xeno organs, to, you know, more futuristic stuff in terms of creating entirely new DNA sequences that can do futuristic stuff, whether that's, you know, microbes that can digest plastic, or directly producing fuels, or, you know, even using new species to colonize other planets. When you get into the area of sort of developing the unknown stuff, there's really, you know, we're going to look for something entirely new. Where does that begin? I mean, is it about sort of working backwards from extremophiles and, you know, looking for the toughest of the tough that exist on this planet and sort of backing into something, or is it about sort of just random, and I'm using the wrong terms here, but mutating these genomes and seeing stuff that pops out of the under end and screening what it does? How do you, you know, I've always been fascinated by like the ability to find completely new things that we never thought of. How does it, what's the process by which we go through something like this? Because it's really some of these new uses, you know, especially when you think of, you know, you want to send a new species or a species that can survive on Mars, for example, before we get there. What's the process of like something like this? It's really a fascinating thing. I just want to wrap our heads around it for some people that are unfamiliar with the topic.
I wouldn't be so immodest to say that the things we work on are things that no one has ever thought of before. It's more like they haven't fully reduced the practice, or in some cases they thought of it and discarded it. Sometimes they either thought of it as science fiction or it literally was science fiction. But there's a big leap from, you know, having a vague thought and bringing it all the way to market, including the social engineering of making it marketable and desirable. But we kind of work at all these stages, from the science fiction brainstorming. Some ideas we come up, we do think we're the first to think of it, at least for a while. Sometimes we'll find that somebody thought of it in the 1930s or something, but it usually in a very vague form. And then how we work on it is not so much working backwards from extremophiles, but we work backwards from what functionality we want. So, you know, we say, well, if we're on Mars, what would we be complaining about? You know, what would we be complaining about? The low gravity and the consequences for our bones and our body fluid distribution. You know, going there, we might be wondering what organisms we can or should bring with us. In other words, we want to keep that to a minimum so we don't contaminate the planet, or it's an opportunity to have an environment that has fewer pathogens in it, or maybe no pathogens. If there are no pathogens, maybe there's less inflammation, less immune, or we have to do something to compensate immune. So you basically start working backwards from from a realistic, as realistic a projection as you can of what the problems would be or the opportunities. And then you start trying to say, well, what technologies would that require? Especially fundamental technologies that you could repurpose for a variety of different things. So a lot of the technologies you work on are things where you can improve by many factors of 10, like 10 million fold improvement in reading and writing DNA. And that affects multiple fields. So it's not like reading and writing DNA only helps rheumatoid arthritis of the knee. It helps essentially all forms of medicine, all forms of biology, agriculture, even non-biological things. So that's what we're kind of looking for. But we're stimulated by specific problems like, malaria makes us think about gene drives. The discussion about artificial intelligence makes us think about, well, what about enhanced natural intelligence? That's already pretty dominant way of approaching things.
I agree with you on that. Sticking then with this science fiction theme for one more question. And this is where, coming from sort of the introduction when I spoke of sort of novelty. And whether that's woolly mammoths or dinosaurs or Neanderthals or a list of other stuff, I think back. I don't know if you read the original sort of Jurassic Park book. I know everyone's seen the movie. So there's this wonderful part of it where Hammond is going around to venture capitalists trying to sell his biotech ideas, and they couldn't care less about cancer cures and this and that. But they love the topic of these, what they refer to in the book as consumer biologicals, these biologically created products for consumer use. And, frankly, I love this topic, not just because it's cool and because I like science fiction and comic books and things like that, but I do look at scientists like you as the real celebrities. Yet I think in many ways the public has been desensitized to biotech. They hear about something hot in the cancer field on TV, and in the back of their mind they think it's 15 years away. They hear about a frost-resistant orange variety, and that's on a plantation in Florida somewhere. It doesn't impact. They don't think about when they drink their orange juice and so forth. Take us just a little further, if you will, about the rest of the science fiction dreams that you can talk about today that are confidential, but and the possibilities you'd like to see materialize in the next, when you move beyond human health, after you solve aging, what are the things you really think might be doable in the coming couple of decades along this novelty consumer front? Because I think we're there, pretty close to seeing some very interesting stuff. I'd love to hear it from you.
Yeah. Well, so one of the things we're increasingly consuming is information processing, and there's this often unquestioned optimism about silicon-based methodologies, even though silicon has sort of plateaued in its growth curve. It was on an exponential growth curve in terms of miniaturization, and that's largely plateaued. It doesn't mean that it's over. It just means that it's shifting into sort of atomic precision, because you got it about as small as you could get with the shortest wavelength multi-billion-dollar super clean room fabs. And that was on the order of 15 nanometers, while atomic scale is sub 0.1 nanometer. And that means that we're in the realm of biology, because biology has been making atomically precise objects for a long time. And so the consumer goods that we can make, in principle, any consumer good we currently make could be made biologically. Even things where it doesn't make, you say, why make that atomically precise? It's just a block of wood or something like that. Well, it turns out wood is biologically made, and it is close to atomically precise, and it's a perfect example. But more and more things will be smart objects that will be able to record information, be able to transmit and respond to and change shape and change functionality and so forth. And I think all of this will be far easier to do with biological systems and with silicon-based systems. So I think that's a whole set of consumer goods right there. You know, it depends on what you mean by consumer. Consumer kind of implies an entertainment component, but historically, consumer meant that you needed to have the supplies to do wagon trains out west or the ship across the Atlantic Ocean. And I think there's going to be a lot of that consumerism that allows us to colonize our solar system. There are many moons that have more water than Earth does, liquid water. And so it's going to be very attractive, and it's very unattractive for us to sit on Earth just waiting for the asteroid that wipes out all living things. So anyway, those would be two categories of consumer-related things, and there's a surprising number of things that have rapid design loops. I mean, anything goes through the FDA. I totally agree. I'm a big fan of the FDA, but it's going to take a decade from inception to full approval for mass marketing. But there are many things that either impact health, like matchmaking to get rid of Mendelian diseases, which cost millions of dollars per child affected, and 5% of the population has an early or adult onset disease of that nature. But that can be done. That can be done with something that's essentially not medical in the way it's executed, but it has huge medical consequences, and probably not FDA of any consequence to them. And there's some other things. For example, if we make biological computers, at first that sound, if you focus on the idea of human neurons outside the body, it sounds like, oh man, maybe that could be FDA. But if you're really just talking about the mapping onto computers in a way that takes the big advantage of natural neurobiological systems, and that may not be FDA. It may not be. It could be just as fast or faster turn time as conventional inorganic computers.
Sure. It's going to be a fascinating few decades. Before I let you go, I just have to move completely now into the area of science fiction, but I need to ask you, who would you, if you could go in my imaginary time machine over here, what historic figure would Dr. George Church want to meet and talk to? Einstein, Newton, whomever, you can pick anyone you want. Who would it be for you?
Yeah, that's a tough call, because I'd want...
You can go to the future, too. I don't want to keep you in the past. If you want to go to the future as well, you can.
Future.
Yeah.
Well, that's even harder because I don't know their names. I think Marie Curie would be interesting to talk to. I don't think she was necessarily labeled as a futurist or visionary, but she made some pretty big impact in the two fields that have impacted me. I think that certainly Linus Pauling and his students, a few of his students I've interacted with, like Alex Rich, who trained my advisor, Sung Ho Kim. So that whole lineage going back, Linus Pauling was a remarkable person. both. So I happened to pick two people that happened to get 2 Nobel Prizes each, but that wasn't the reason. It was just in different fields. I think I'm impressed by people who have this sort of interdisciplinary approach to the world. I wouldn't mind meeting Nikola Tesla. I think it would
Mm.
be interesting as well. Some of the people I'd like to meet were notoriously not communicative, like Dirac, but still, you know, there you have it.
Thank you so much for joining the show today. Dr. George Church, Robert Winthrop Professor of Genetics, Harvard Medical School, Professor of Health Sciences and Technology, both Harvard, MIT, and founding member of the Wyss Institute for Biologically Inspired Engineering. Everyone should pick up his book, eGenesis, How Synthetic Biology Will Reinvent Nature and Ourselves. It's been such an honor having you here, and thank you once again for sharing your thoughts and your knowledge with us and spreading these wonderful ideas. And it's what the world needs.